Okay, so this is the section 7.5, and this is work part 2. And here we're going to hit a slightly more complicated set of problems. Remember, we talked about work is force times distance for constant, or in our case, it's going to be the integral of your force times your distance dx. Okay, so let's take a look at an example of these types of problems. So what we've got here is we're pumping water out of a tank. Over the top, and it makes a difference whether you're taking out over the top or from the bottom, and I'll show you why. And if you think about this intuitively, it should take more work to pump something out over the top than just to open it up at the bottom and let it go out. So the tank we've got is a rectangular tank. Its base is 4 feet by 5 feet. And it's 6 feet tall. Excuse me, it's 4 feet tall. All right. The water weighs 62.4, to be 62 pounds per cubic foot. And this is pretty typical for fresh water. Salt water is a little bit denser, it's 65 point something. All right, so the most important thing when you do these things, the most important step heard me say this, but this is true here. Draw the stinking picture, even if you've got one, because you're going to need to mark it up. So what I'm going to do is draw my tank in cross section. All right, here it is, and when we're full, this height is 4 feet, and this is 5 feet, and of course it goes back 4 feet and goes up. All right, so what we're doing is we're taking our water out and we're pumping it out over the top of our tank, and then it exits out at floor level. All right. So the second most important thing to do with this is just to pick some spot somewhere in there and draw yourself a little disc. This little disc is going to have a height of dx, infinitesimally. Okay, so the first thing we want to do is find the volume of this disc. And the nice thing I notice when I come down through here, this problem is going to be a lot easier than the next one, because no matter where I draw my disc, the volume is going to be the same, because they're all rectangles and they're all the same. So the volume of my disc then is going to be the area of my base, which is going to be 4 times 5 times my height, dx. Okay. Now, the other thing then is I'm going to set my x up here as being feet up. So there's my x. Now, when we're pumping this thing out, this disc is actually going to have to come up and out, all right? In other words, it's going to be lifted up before it comes back out of the tank. And so the distance my disc travels is going to be 4 minus x, because it's 4 minus whatever my height is right here. Okay. So now at this point, we're sort of ready to go back in, except we don't have a force. All right? So what we need to do is basically find the weight of the water in my disc. And that's going to be equal to the 62.4 pounds per cubic foot times my volume, which is going to be 20 dx. So that's my weight. And the distance moved is going to be 4 minus x. So the work done for my little individual disc, and it's going to be the weight of the water, which is 62.4. And I'm going to go ahead and multiply these on out. That's 1,280 dx. That's my weight of my water. So this is my force. And then my distance then is going to be 4 minus x. All right, and I'm going to rewrite this to make it a little bit nicer. 4 minus x, because we're used to seeing our dx at the end. Okay, and so to find the total amount of work done, we're going to integrate this thing. Now our bounds, you have to be a little careful. So when I start off, and the first part of this, let's do part A, because up to this point it's basically all the same. So in part A of this problem, we want to half empty the tank. Now remember, we're integrating from this distance up to my disc. So when I start off, x when I start is going to be 0 feet. All right? In other words, I start with everything at the bottom. And then x at the end, if I'm going to half empty this, then is going to be at 2 feet. So I'm going to have my work total is going to be the integral from 0 to 2 of this 1280 times 4 minus x dx. Should pull this out. And then you're going to have to integrate this thing. I'm not going to do this for you. It's just a simple little rewalk rule. And it comes out to be, oh crud, hang on. $2,496 foot-pounds when you integrate this out. This is to half empty it. So part B is to fully empty. All right, now nothing is going to change at all until we get to this point. So my X start is going to be at 0, but my X end will be 4 feet up. It's going to be 4. So the only difference between that one and this one basically is our bounds of integration. So our work total then is going to be equal to, it's 1280 times the integral from 0 to 4 of 4 minus x dx. And when you calculate that, that worked out to be 9,984 foot-pounds. Okay, so now let's take our same basic problem. I'm going to show you why it makes a difference. And now instead of emptying from the top, we're going to empty it from the bottom. All right, we've got the same basic idea up here. We've still got our little disk, which is going to be a distance x up. The individual weight of that disk, which is our force, not our work, that's our force. So the individual force we're dealing with, which is the weight of that, is still going to be the 12,080 dx, which is my volume times the 62.4. Okay, now the distance, this disk is going to move, is going to be x. So not only that, it makes our math a lot easier. So what we're going to have then is I'm going to have the integral, and to completely fill it, x is going to go from 4, actually, what we started with, to 0 of my 1280 x dx, which is negative the integral from 0 to 4 of 1280 x dx. I'm not going to calculate that. But as you can see, we actually gain some work because gravity is going to be doing it for us. So it does make a difference. If you're draining over the top, you have to, remember, you have to lift this thing. When you're coming on the bottom, and so you have to deal with how far up you lift it. Deal with the bottom is just how far it has to drop. Okay, so now let's deal with a completely different type of problem. And on this one, I've got a conical tank. And these things are a little bit of a pain initially. Once you see, or you should see, once you see the, and again, this is containing water. And it's at 62.4 pounds per cubic foot. Okay, and what my tank looks like is this. It's cone shaped. It's 8 feet across at the top, and it is 6 feet high. Okay, now, so what we're going to do is take our little slice out of here. Now you notice my volume changes here. Now my slice here is basically, if you think about it, it's going to be a right circular cylinder. And the volume for that is pi r squared h, okay, where this is r. Now, I know r is going to start off at 4 at the top, but it's going to be at 0 at the bottom. So this is going to change. My h is going to be my dx, where x is my distance up. Okay, so the trick to doing these is to imagine you can take a slice right down the middle. So what I'm going to do is look at a cross section of this cone, slice down the middle. I've got a right angle here. This is 4. This is 6. Here's my R. And this is X. So what we've got are two similar triangles. I've got this little one here, and then I've got the big one here. And if you remember, with similar triangles, you could get this stuff by setting up your ratios, which would be 4 over 6 will be equal to R over X. And normally we go ahead and reduce that. Okay. Now, so my volume is pi r squared dx. What I really want to have in here, and my r is a function of x. It depends on how far I'm up. So what I'm going to do is cross multiply. I have 3r is going to equal to 2x, or r is 2/3 x. And I'm going to substitute, so my r of x is going to equal to 2/3 x. And I'm going to substitute that back in then for my volume. So the volume of my little disk then is going to be pi times 2/3 x squared times 62, times, getting ahead of myself, the height, which is dx. So my force, which is going to be the weight of that water, then will be 62.4 pi times 4/9 x squared dx. My distance is the next thing we need to take a look at. And thinking here is exactly like what I did on the other one, which is that if I come back in and take a look at this little disc right here is going to have to be lifted up of this part because we're pumping it out of the top. So my distance is going to be 6 minus x. So my individual work then, the work done on that little individual disc then is going to be my force times my distance, which is going to be the 62.4 pi times 4/9. This is all constant, times x squared dx. So all of this will come out front. You'll have to do multiplication and blah, 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 blah. So now to get my work total, I'm going to have to integrate this thing. And when I start, x is 0. And if I'm going to empty it, then my end, x, will be 6. Remember, that's the distance up we're coming. So it's going to be integral from 0 to 6. I'm going to go ahead and pull all this mess out. 62.4 pi times 4/9. And then the integral from 0 to 6 of x squared dx. And when you pull all of this together, the work came out to be 2,995.2 pi foot pounds. Okay, so in summary then, steps, and skip a step, and risk missing the problem. Even people who have done this for decades still go through all of these steps. So the first one is to draw a cross section. And the second one is take a very thin slice. It's going to have a thickness of dx. Then see if volume changes with height. If so, set up similar triangles and solve for your R. Now, if you take a look, most of this is geometry. There's not just a whole lot of algebra or calculus in all of this. Step 4, find the distance your disk has to be moved. And then step number 5, your individual work then is going to be the individual force on that disk times the distance. Step number 6 is you integrate your individual force over your balance. Okay? So be sure you go through all of these. I can almost guarantee you right now, you guys are going to want to skip this one. You're going to want to skip this one. This is a pain in the rear. It's a bunch of geology you're going to want to skip one. You're going to skip right down to here and make a serious mistake. And you will be awarded 0 points. Do all of these steps. I mean, draw all of them. Do every one of them in order. I've known people that have done this kind of thing. Some engineers have done this kind of thing for 40 years, and I still see them do the same thing every time because it helps them focus on the problem. It helps them see exactly what they're doing, and they are less likely to go in and make a mistake. Now, the reason we're interested in the work is that is related to how much energy it's going to take to accomplish this particular task. Okay, so again, be careful. Do all of these steps. Do not come down and say, oh my God, drawing, yuck. Take a very thin slice. I can do that in my brain. Draw this stupid thing. Volume change. Ooh, no, that is geometry, so I'm going to skip that one. Find the distance your disk has to be moved. I'm just going to call it X. So you're going to come down, you're going to number 5, and I'm going to chortle all the way. Well, I give you a big old fat enchilada, a big 0 on that problem. And if you don't think I will, try me.